Here is, in each of these sections where we have the bending magnet, where we change the trajectory of the electron, we apply a force on the electrons, an electromagnetic force, so causing it to turn. But really, and this is where even it's beyond my comprehension, but this guy has formulated everything that is needed about it. Relativistic effects causes X-rays to appear once you apply a force to the electrons at the relativistic speed. So you just get a very sharp X-ray in the direction of the velocity here. And nowadays we also have various insertion devices to manipulate the trajectory of the electron even more. You have so-called wigglers or undulators, which you might hear about if you go to a synchrotron. And it's only magnetic arrays to sort of change the track of the electron even more and causing better X-rays. I would just call it better, more focused, more intense, more coherent. So this is more or less the principle. We just bring around these electrons, we change the trajectory, we generate X-rays, and of course to extract these X-rays we build experimental stations where these X-rays are generated, which are called beamlines. Might also be a word that you are familiar with if you have been at synchrotrons. Basically you stick a pipe into the ring and extract the light, and then you have the light that you want to use for various studies. And by the way, if you have any questions, please interrupt me. This is supposed to be like an informal setting, and I can talk and talk, but and I won't go into details, and I don't have a whiteboard to draw anything, so those questions we'll do some other time. Okay, but this is the basic principle. We generate X-ray. Yes?
So it's actually the X-ray that's doing this. It's not, I mean, the whole thing that you're turning it is just so that you have enough like energy when
yeah, so the purpose of a synchrotron, it's all so-called synchrotron light source. It's the source for creating X-ray light. So basically what a synchrotron is a laser pointer but with X-rays. So you have this, you create very focused, sharp light, but with very, 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 very small wavelength compared to this. But that's the whole purpose of this huge facility. It's a little bit bigger than my laser pointer for visible light. But that's it.
Why don't you do it directly?
What?
Why don't you just directly shoot the X-ray?
No, the X-ray is generated by the circulating electrons. So the electrons is the sort of source of the X-rays. But we stick a pipe there to extract the light that is being generated there anyway because of the bending of the electron trajectory. Is that answering? Yeah. So we are not interested in the electrons here at all. We are only interested in the X-ray light. So it's not shooting electrons at stuff. That's other techniques that are doing that. But we accelerate electrons just like we do in old time televisions. We know how to accelerate electrons. That's something we have done a long time. But extracting the X-rays, it's a lot of energy being consumed anyway by driving this, and that's why they are built. And typically also the energy is proportional to the radius sometimes. So you have bigger synchrotron and more energy also generated. And yeah, so why X-rays? That's next question. Okay, we have a laser pointer with X-ray light. Okay, what can we do with it? And the purpose is to look at small stuff. Okay, so we build this huge billion-dollar facility to look at things very, very, very small. So why do we do that? We have techniques for looking at small stuff. Why do we need a synchrotron light source? Well, if you use other types of light, for example visible ones in a normal microscope, you encounter some difficulties because of the finite width of visible light. What happens when you start looking at stuff smaller than the wavelength of the light, it starts to diffract, and you start getting blurry images, and you can't get the image information out of it. We'll come back to how you can actually utilize this diffracted light, and you can do that also for visible light techniques. You might have heard something like DLS, which is dynamic light scattering. So where you use laser visible light and you gather information about the scattered light, which you use, I mean, if you've been in a chemistry lab, use it for size determination and these things. But also problem with scattering of visible light is the fact that you have multiple scattering. So scattered photons will scatter of other stuff in your material, and you will just see there will just be a blurry scattering image as well. So you usually need to have dilute samples. You need to add more water to your sample in order to run it in the DLS to get some useful information. So these are some restrictions on sort of just why X-rays instead of visible lights. Okay, what about electron microscopes? We have maybe heard about SEM or TEM, where you can use electrons and shoot directly at your sample. Why don't you do that? Well, it's a very powerful technique, I must say, and all the things that happen within cryo, you can really freeze your sample and look really at atomic level with these things. These are super high resolution stuff. But usually they have some issues with very strict with sample environments. You usually have a sample holder with a small thing that you put into a vacuum because the electrons are very easily diverted by if it's not in a vacuum. So it's very strict on sample environments. And often you need contrast agents as well. I know that when we look at these cellulose nanofibrils, we use some uranyl acetate to increase the contrast. So you need to do some sample manipulation, and you also, I wouldn't say any more restricted to dry samples, because there's a lot of things happening right now with also liquid TEM. So it's improving, and it's a technique that will also continue to improve alongside with the synchrotron. So it's not that we will do synchrotron measurements instead of this always, because they will complement each other. Okay, but X-rays, the good thing, super small wavelength, no problems with the whole diffraction limitation stuff. It's highly penetrating. It can go through a lot of material without being easily blocked or reflected like visible light do. Does not also need a closed sample environment. So at these beam lines you can basically put whatever you want in front of the beam. It doesn't need to be a vacuum around it. And you shoot X-rays through it and collect data on a detector behind it. So it has definitely some advantages here. And I'm going to talk about the two main techniques available for soft matter research. This is because I would also like to stress that there is a lot of different techniques available at the synchrotron. Soft matter is only a small part of that. Mostly people are looking at solid state stuff, crystallography, metals. But when you work with soft matter systems, cellulose, like I have done, it's usually these techniques you encounter, imaging and scattering. And so that's what I'm going to talk a little bit about, and what is the difference, and why do we use the other and not the other. So imaging, this is, I guess, what you would refer to if you think doing an X-ray image. You would think about something like this, where you have density differences inside your sample. Some things absorb more than other things in your sample, and that's how you can build up an image, just because some things are absorbing more light than other stuff. So this is the basic principle. Then the sample can also manipulate the phase of the X-rays. I won't talk too much about that, but there is phase contrast imaging as well. But mainly it's differences in absorbance. You will collect the light on a detector, and you will see some areas having less light reached to it than other. And if you rotate your sample, You place it on a rotational stage. You can do tomography. And I would also say that it's really the sharpness of these beams that makes it possible to do this type of imaging on almost nanometer level nowadays. So you get like a nanometer scale of your pixels, which you don't get with a medical X-ray for sure, how much you try. So this is, it's like a light bulb compared to a laser when we look at visible light. That's sort of X-ray sources in the hospital compared to the synchrotron. So yes, we can do imaging, we rotate the samples, we look at differences in absorbance in your sample, and you can do a reconstruction and get the three-dimensional structure of your sample. So yeah, I brought a tomogram that I did for my master thesis 8 years ago, which is a carbon fiber network here. And you can see exactly how these lie around, and for my case I did fluid simulations through these materials. So you can combine a little bit like that. So it's quite neat. You can even make it time resolved nowadays. I find this example is so pretty from Switzerland. So basically they put a fly on the rotational stage, rotated it in front of the beam, matching with the frequency of the flapping wings, so that you take images with a little bit of delay so that you can get all the faces through the flapping, and then you can really dig into, you can make these cuts through the fly while it's flapping its wings, looking exactly how the muscles are working within the fly, and yeah, gathering biological information from this. So you can do these measurements.
How long did the fly stay alive?
Yeah, probably. You should read this. I don't remember that, but of course, I don't know how many cycles it flapped its wings, and if there are any ethical consideration additionally for this. But anyway, it's interesting. You can do stuff like that as well. Time resolved tomography. But imaging has some fundamental problems, which is fundamental for all types of imaging, like microscopy, electron microscopy, regular microscopy. And that is the thing, if you want to increase the resolution, you zoom in. I think that's a concept that you're quite familiar with. You want to get even smaller features, you zoom in. But always when you zoom in, you lose field of view. So the more resolution you get, the less statistical significance. Because how do you know that this is what your sample looks like everywhere? And you will always have that problem when it comes to imaging. What is the statistical significance of my image? And with tomography, it's even more problematic because I did this master's thesis, you already saw it was some kind of paper, some kind of two-dimensional more or less structure, but it's not allowed to stretch out too much in one direction. It should be somewhat similar absorbance regardless of rotation angle, which means that if you want to zoom in tomography, make nanometer resolution tomography, you need maybe a micrometer sample. Which is very difficult to handle. A piece of hair is like 20 microns or something like that. So something on micron scale is just very tricky and will easily burn also in the X-ray. So degradation is a whole different part of it, which of course you can always think a little bit critically also how much are we influencing the sample during measurement. And this, I won't talk too much about it here, but there are definitely considerations on that aspect as well when we use X-rays. But okay, this is the fundamental problem one with imaging. Another problem with imaging is that if you place too much stuff in the beam, you would just not see anything. So you can have more particles. Let's say that we want to study elliptical particles like here, like I automatically generated. Okay, here we see clearly length and width of the particle, maybe how they are arranged. Adding more particles in the beam, then you will maybe still distinguish that there are elliptical particles here. But adding more and more and more, you come to a certain point where, well, this is a blur. Is this elliptical particles? Really difficult to tell, right? And this makes it problematic. You need to also be at least very dilute samples, spread it out so that you can really image it to see any contrast. Another problem with imaging, always there, is exposure time versus dynamic time scale. So if you have stuff moving, that motion must be far slower than your exposure time, because if something moves during the exposure, it will blur out the image. So if you have very fast exposure, you expose it fast, collect the data, maybe you will get something like this. And yeah, you could tell that these are elliptical particles in your sample. But yeah, if they are moving a little bit faster compared to exposure, it will just blur out, and you will not get any information out from the image. And adding these two problems on top of each other makes it basically impossible to image anything, for example, nanoparticles moving in a liquid. That's not fast enough. And because we are talking about nanosecond timescale of the motion, Brownian motion of nanoparticles in water, for example. So this is quite limited to dry samples. But okay, we want to do soft matter research, maybe like dispersions, gels, something, especially here within the Wood Science Center. So what else can we do? Oh yeah, I just put this image up to just illustrate exposure time versus dynamic timescale. I forgot about that, but this is really pretty, I find. So sometimes you can get some information out of the high exposure image anyway. For example, the location of the Polaris star by doing long exposure photography. So these are the things, but you might lose information that these are actually stars. Okay, so these are some fundamental problems of imaging. And the way to address many of them is by using scattering instead. So scattering is a very powerful technique. It might look like a blurry image, this too, and wonder how do we get any information out of this then? I mean, we just saw this. You just said that we had a lot of blurry images and we couldn't get anything out of it. Well, the scattered light is actually a tremendous amount of information there that you might not think about, and I will go into what it is. Because one single exposure gives you information. So one single exposure gives you statistical information from the molecular scale, like angstrom scale, sub-nanometer scale, to hundreds of nanometers. So statistical information. It's like you analyzed all of these zoomed in images all at once, but you just do it with one exposure. So that's the power of scattering techniques, really, that you get this statistics out of it. And you can get information out even if the sample is moving crazily fast. You are not limited by this blurriness or the other, what was the other thing? Yeah, a lot of material in the beam. That was mainly the thing. And I chose a way to demonstrate this exactly. I want to see if this makes sense to you as it does to me. Because what scattering is really, this is the Fourier transform of the image. So they are related. The imaging and the scattering techniques are related. But you have, what you see in the scattering image is just a Fourier transform. And okay, so what is the Fourier transform? Well, it's often used in signal analysis. So if you have a time-dependent signal, you might have like something like a sine wave with a certain frequency and plus another sine wave with another frequency. And if you add them together, you will get this sort of sine wave with small features. You see these small wiggles correspond to the shorter time. And if you Fourier transform such a signal, you will get two peaks, right? You get the low frequency, which is the long waves here. And then you get a short frequency. So a high frequency, which is the short wiggles. And the amplitude is related to the amplitude of the signal here. So it's quite easy way to filter out information from this time-dependent signal. You Fourier transform it and you see directly the amplitude and the frequency of the wave. So I think this all makes sense when you talk about time-dependent signals. The problem is that it's exactly the same for scattering, and it's somewhat sometimes not as easy to comprehend. So we can just switch. I say here also, the angular frequency is related often to 2 pi over t. So where you have if you have a time here, the Fourier transform is usually talking about angular frequency omega. Okay, so let's just switch symbols. We replace t with spatial coordinate x, measuring something in space instead of time. So we change the period to being a spatial period instead. We say the signal, we can call it sample density, for example, that you have some density variations in space. And then do exactly the same. I have not done anything else than change the symbols here. And when we Fourier transform it, we get a spatial frequency instead, which is measured in radians per meter instead of radians per second. We use a symbol called Q instead of omega, but it's the same thing. It's the angular frequency in space. Okay, so we get a peak there for x1 and one for x2. Nothing else. Change it about just the labels of everything here and the symbols. And this is the thing. This usually is measured. We measure frequency in something like hertz or second inverse. So 1 over second. How many periods over time. When you do this in space, it will be inverse meters or inverse nanometers or inverse angstrom. Same sort of thinking. Think about frequencies and how that relates to length. Okay, so this is what we measure in scattering. We Fourier transform the image to look at what type of frequencies we have in the sample, spatial frequencies in the sample. So let's do it like an image instead. So maybe you see it two-dimensionally, it will make sense. So we have the same sine function as I showed before, but I made it two-dimensional, just stretched it out in one dimension, where white is 1 and black is 0. This might be the image of your sample. You have density variations like in the imaging, where you have small features and large features. And Fourier transforming it, I don't know if it really is easy to see, but you will get a peak there and peak there corresponding to the frequencies here. So the one close to the center here will be measuring the large scale frequency, and the further away from the detector center is measuring the smaller stuff. And I can even do like this. I will remove every negative thing because negative densities. We stay with positive everything, so just set everything to 0. We have some additional frequencies, peaks showing up here, but you still see very bright intensity here and here, corresponding to the two length scale here. You actually get a third length scale, which corresponds to the emptiness, the structure of the emptiness as well, because the scattering can't really determine what is what is the dense part and what is the non-dense part. It will just measure density variations. Okay, so let's do it like this. Then if we take this sort of image, we can see the same information in the image. Why would we even bother doing the Fourier transform? Makes no sense. We could have just done the image here. Well, the interesting thing is, let's say that we generate this sort of structure, lay them on top of each other as if it was a very dense sample that we were looking at. So we have the blurriness effect, or maybe it's because of motion. And we look at the Fourier transform while adding stuff to this. So yes, the image becomes blurry and blurry and blurry. but you still get the frequency information out from the Fourier transform. So you see this as rings on your detector. You will see that, we have some small features corresponding to some periodicity on that length scale, corresponding to the scattering angle here. But if we look at this image, it will be very difficult to tell what this was initially. So that's sort of my demo here a little bit about differences between imaging and scattering. And why it's so powerful for soft matter, that you can get this out, even though an image would give complete blur. Scattering is basically you shoot at the sample, you collect data at certain scattering angles, usually divided up into small angles and wide angles, where the angle will tell you what sort of structures. Here we look at small structures, high spatial frequencies. Here we look at large structures with large frequencies in your sample. So here we have information from 10 to 100 nanometers usually in what is called small angle X-ray scattering, SAX. And here we have information maybe from angstrom to tens of nanometers. You can look at molecular arrangements and these things, which is contained in the wax signal. And Q, more specifically, is related like this to the scattering angle. It's 4 pi over wavelength times sine theta over half. And this is directly the spatial angular frequency. So you can look, okay, from a certain angle and wavelength here, you can determine what frequencies can we actually look at with the current setup. If you want to look at even smaller things, maybe you will place the SAX detector even further away, because just to resolve those frequencies. Okay, so for example, if we look at cellulose nanocrystals, you might get a radial this is a radial position, Q, and spanning all the frequencies. We might see on the higher frequencies here, or here you see the length scale on this axis and the frequencies here, so you just understand a little bit. Here we're at 0.2 pi, so 0.6 angstrom level. We see some peaks here, and this is corresponding to the cellulose molecular arrangement inside your nanocrystals. So we can see they probably have some hexagonal arrangement. We see these peaks. And then if you look at moderate angles like here, you will get information about the cross section. So it's like zooming out from the image. What do you see then if we zoom out? Oh, well, we see these are flat-shaped particles on this scale with certain cross-sectional dimensions. And if you look even further, you might see other periodic structures appearing on the larger scale. So for CNC, we know they arrange in these chiral, nematic, tactoidal stuff. And they have then very periodic arrangement. And this you can see by comparing dilute and concentrated samples. And you can tell, this is due to the large scale structures. And you can start seeing, what is the distances in this sort of formation. And this is all from one exposure. And it's statistical. And that is the key point. You get all of that in one exposure. So average over millions of particles in your beam, or how many it can be. Okay. Well, that was only talking about material characterization. Basically, you put material in like a capillary, and you get all that information when shooting X-rays and collecting the scattering data. But yeah, this is where I thought it was really fun, because you can do all types of in situ experiments as well, because you can place basically whatever you like in front of the beam. You can put your entire experimental setup in your lab and put it in front of the beam and get the same sort of information during some kind of process. For example, during flow, what happens in certain flow situations to your material? How does the structure on all these levels change? And with mixing, if you mix another chemical, how does this arrangement change? or having thermal or electric and magnetic or pressure or tensile. You can have all these, expose the material to many conditions and study what happens with structures during that time. And this is where I hope you are like this now. Oh my God, there's so many ideas here. So much to do at the synchrotron. My material probably will be very good for these sort of measurements. So this is at least what I'm hoping is sparking here. At least this is me 2 years ago for sure, and still I would say. It's too many ideas, not enough time to realize them all. But it's quite useful for things. And this will lead me to the next part, the how. How will you go around now? Okay, I have a super idea. Perfect. I wanted to ask, are there any questions at this point? Yes?
Yeah, would you maybe sum the 3 problems with scheduling, since you have summed up the 3 problems with imaging?
Well, for one thing is, okay, you sort of have these frequencies, but it doesn't tell you the exact shape of your sample anyway. It's sort of without any imaging technique like AFM or TM or something, you might end up just, okay, this looks like a sphere, but I know it's fibril somehow. And this might be because some frequencies can overlap and it might look like something else. You need some prerequisite knowledge about your sample before doing scattering. So doing a CTM, this looks like a fiber system. So then we know, okay, the only frequencies we will look at will relate to the fiber cross-section and fiber arrangement. The length of the fiber is too long to be resolved within this frequency, so we know the length of the fiber doesn't matter. It's just the cross-sectional information, and so on. So I think that's where sort of scattering has a big problem. Nowadays, when it comes to certain imaging techniques, there can be higher resolution, especially visible light techniques. It can have extremely fast measurements, but synchrotron speeds up when it comes to just time resolution of your samples. But nowadays you can do coherent scattering, just like DLS, but with scattering instead, X-ray scattering instead. But it goes down to millisecond time scale, while DLS can measure a lot faster than that. And we have other problems. Degradation it's really dependent on what you want to look at. If you assume structures of some kind, you can have your Sachs and wax measurements confirming the scales of those structures. I think it's not. It might be difficult still to say what this is, but we know from TM images what a cellulose nanocrystal look like, and that's how we can sort of determine, okay, what could these frequencies be in the sample on this scale. But it's not one method. You should probably, and this is within material characterization, you never should rely on one measurement technique. You should have some confirming your data and giving more evidence to what you're proposing. Is that helping? I haven't really listed them in the same way because, of course, I've been doing scattering and I love it. No. There are no problems. But degradation and beam damage, I think, is the main thing that always need to be whenever doing X-ray, whatever, imaging or scattering. So you could try different levels of exposure, see do you get the same results, and so on.
Isn't it also easy to misinterpret your image?
Yeah, and that is the key point. If you assume spheres, you will get a dimension of the sphere from the same. If we didn't know anything about this sample, we could probably fit the data with a polydisperse spherical distribution and then say, oh, this sample is spheres, and yeah.
And I think that's a big problem. People publish things,
yeah,
and then they just
just use whatever model.
Exactly.
and then say a dimension of something.
Just because it's a fancy technique.
Yep. And that is so true. And should be critical. And if you ever get to be reviewers, that's what you should comment on.
No, but I mean, that's general.
Yeah.
Any measurement data you would interpret, you are model dependent.
Yeah.
So, I mean, it's not specific
No.
to this technique.
No. Exactly. Any more questions before the how? Yes?
Another comment that you also you don't need to look in bulk with scattering technique, you can also look at the surfaces.
Yes, good point. I haven't even touched upon grazing incidence stuff here, but even if you have a non-penetrable stuff, you can place it like this in the beam and just have your beam bounce off the surface and get same sort of statistical information about periodicity of your surface structures. And that is definitely key here. I only talked about soft matter so far, and grazing incidence is a big deal as well, for sure, in these facilities now. Yeah?
How thick could the sample be?
For transmission?
Yeah.
We usually, I would say,
I guess it depends on the...
it depends, I guess, on setting on the beam. And I think this is where you should, I will come to that, talk to the beamline support, what your sample looks like, and is it feasible? Because, for example, like the carbon fiber network, and we did an in situ fuel cell in the beamline, that was like almost a centimeter thick and was no problem of doing tomography of that. And the fly is also on almost centimeter scale.
It's around that.
But of course then you lose resolution, so that's dependent on the detector. What is the pixel size of your detector and your beam size and so on. So yeah, I think you can, I mean, X-rays are penetrating but not really like, it still gets blocked. If you put a piece of lead there, you won't see anything. It will block everything. So it can't be too penetrating if you really want to see something through it. But there you have neutron techniques, which I won't go into, but we're also building an excellent neutron facility next to the MAX 4 lab. And neutrons have the fun stuff that they can penetrate through metals and everything and suddenly just scatter off water. So you can look at a water droplet inside a big block of aluminum because to neutrons, the aluminum is transparent. And I find, but that wouldn't work with X-rays. I mean, the aluminum would just block out everything. X-rays are only dependent on sample density or electron density more specifically. So the denser material, like gold, uranium, will interact a lot with your light. It will block, absorb, scatter a lot. While other stuff, less, like just periodic table go through. But neutrons are isotope dependent instead. It's scattering off the nuclei of the atoms. So it doesn't even care about the electron cloud around it. So yes, we will have neutron facility which will complement this even more, and which is why Lund will become a quite cool place for material research in the next couple of years, decades, hopefully. If everything gets built, that where the ambition lies and the money comes from. Yeah. Anyway, so I will go into the how part here because now I spent a lot of time on this, but I actually wanted to spend a little bit more on the why part because I hope this will inspire you more to think about cool things that you can do. So this is the how based on my experience from NSLS2. It might be a little bit different for DC and Hamburg. It might be a little bit different here and there, but more or less the same steps I would still assume that there is. So this is how you go from idea to beam time at NSLS2. Well, first, if you don't want to do it at NSLS2, of course, accessibility is one of the key things. Like, can I go there at all? Like, if it's on the other side of the globe, it's really worth doing a synchrotron measurement in Australia compared to other locations closer, like Hamburg. Or MAX 4 when everything is built there. So accessibility can start off with. scan through what type of beamlines they have. They will list the types of techniques. If you don't recognize technique, skip through. You will see Sachs wax, perfect. They will always have like 1 or 2 Sachs wax beamlines at the synchrotron. So skip all the others. It's other spectroscopic stuff that I have no idea what you do with them. But other fields do. And that is the key point. It's very multidisciplinary. The synchrotron radiation light source is like hot pot of all sciences. So don't assume either that the beamline support knows what the hell you're doing. They maybe have no idea. But you can scan through like, they have a list of publication from the beamline. Like, have they done something similar? Maybe they have worked with cellulose. Maybe you know somebody that has done cellulose materials at a certain beamline. Maybe that's where you should go, because then the support, the personnel know a little bit about the samples already, which reduces time, and they can optimize beam and everything according to, without you specifying what you want. So that is a good idea. Look at the usage. That's also published usually. Like how many proposals they get and how many they accept. If you might have found a Sachs wax beamline, but it turns out they also have this super unique technique that is nowhere available anywhere else. And then it will be so many proposals to that beamline, and you will probably not get beam time. So take a look at the usage, how many proposals they get. It might be better to use a less fancy synchrotron, but that you at least have higher probability to do measurements. Suitability limitations, again, contact. If you found something reasonable, you want to do Sachs wax, can I fit my lab in front of the beam? Or whatever you bring there, or is it really microscopic samples? And this touches upon a little bit, like ask them, we have these samples, we want to do Sachs wax, is it suitable for your beamline? And they will respond, usually very quickly, and say no, or they can say, yeah, this looks good, we have used cellulose nanofibrils many times before, so let's go. They can also like, we are not sure, but can you send us a sample of your material and we can test it overnight and do a feasibility study. And that, sometimes they accept doing things like that as well, because it's quite fast measurement for them to do. But it's a long time for you to go there, set up their experiment, blah, 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 and then you realize, it's not worth it. So contact Beamline, talk about this. It will, you will find the place to go. Then it's time to write and submit proposals. This is how it's divided up at NSLS2, so this might differ from Synchrotron. It's divided up in cycles, 3 cycles, where you have proposal deadlines at the end of each cycle. So this is the deadline for cycle 3, so they have a whole cycle in between to just review the proposals. One proposal is valid for 3 cycles, 1 year, so you can submit time requests for 3 consecutive cycles. I won't go into detail here. That's for a proposal writing course or something. But basically, it's not. I mean, if you have written any kind of proposal before, it's the same information. Why do you want to do it? How will you do it? Who are you and your team? Do you have any prior experience, like publications on this type of material? How much time do you need? Do you need a week? Do you need 8 hours? Preliminary results. About the time that you also can talk to the Beamline support. They might be able to assess it better, or other people that have done similar experiments. Or if you and if you have preliminary results from kind of feasibility of your samples, it's even better. It will give you a better score as well. So that.
Tomas, that is NLS. How much writing is it? I mean, how long is a proposal?
So usually it's maybe 3 sections that are a little bit longer, and that's really the why and how. So you need to put in some, like writing an introduction to a paper. Maybe it doesn't need to be as well written as in a paper. But still have some references, maybe 5-10 references to place whatever you're doing in some kind of context. And And the how part it's a little bit of a project plan. Which steps are you planning to perform? And also, it's usually why do you believe this beamline is applicable for your samples? But usually the entire request is something like 3-4 pages. They have limitations in the amount of words you can write in each box as well, so that's basically setting it. So I think at NSLS2 the how part I think is restricted to 4,000 characters, and the why part I think is 2,500 characters or something like that.
It's longer than DESI.
Sorry, it's longer than DESI. Yeah. Okay. Yeah, but this changes, and the way they actually do the proposals also has changed during my time there. So suddenly they have a new template that you should work with the next cycle. And look, that's a good key. Look at the updated proposal template, because you don't want to write the entire thing and realize that's not the information I wanted. They don't change it that much, but it's still, okay, this is actually belonging to this box now, and this is belonging to that box, and so on. Yeah, but that's basically what you will do. You will write and submit this. You will get a review score. 1 is the highest, and they will just more or less just sort them out at the beamline. Okay, we have cycle 1 requests. These are the scores. We draw the line there. That's if we have worse score than this, you don't get beam time this cycle. NSLS2 does, I'm not sure they do anymore, but some synchrotrons might have aging, which means that if you end up here, like it's really not so fun if you realize that the cut was at 145 and you have 150 and you're rejected beam time. But the key is that once you do a time request for the next cycle, your score will have aged 0.2 points. So you have better chance submitting the second time. So don't assume that, I didn't get any beam time. You can, because the proposal is still valid if you got a score, you can submit again, and some synchrotrons apply this aging. So yes, yay, we got beam time. You will get in contact with the beamline support, consisting usually of a beamline scientist, normally a postdoc doing their research project there at the synchrotron. That's your main contact, and will help you out with all the measurements, teach you all you need to know about the measurements. You have some kind of leader responsible that might step in, and you might also come in contact with that person. They will give you a proposed schedule. Can you do this slot or this slot? Usually you have not more flexibility than that. So don't plan up your entire time in advance until you gotten the review back, or the schedule back. So yeah, it sets some restrictions on your personal life sometimes, because they don't know about weekends or holidays or anything like that. So just deal with it. And it's usually like this in a row. You get 20 multiples of 24 hours usually. So 24, 48, 96, 72, and you want to make use of that. You want to measure as much as you possibly can to gather as much data as possible. So the next thing is now starts the planning. And the more you plan before you experiment, the more successful you're gonna get. I'm completely convinced. You want to know what practical details need to be sorted out first with the beamline. Like, do they have the tools needed, or do we need to bring the entire toolbox in our bags? How about mounting of your experiment? Post-processing, this is also some time-saving thing. If you learn a little bit about their post-processing treatment before you go there, you can learn how to analyze the data while you're sitting there and having the data. You don't need to go there blindly and then hope that you got the data, but it turns out a couple of months later that, oh shit, we did it all wrong. So if you learn a little bit to analyze the data before going there, it helps out a lot. So you can ask them do you have some example scripts, for example? Here they use Python, so you can ask them for Python scripts for analyzing the data. Get some raw data image to just play around with before. So yeah, you get the contact schedule. Now that you know all the restrictions, you make a list. experiment. What is experiment 1, 2? What do we start with? What is highest priority? And lay out as much details as you can. The more detailed this becomes, the easier it will get, because you will get dead tired after 72 hours working in shifts and so on, and people will get annoyed. And so if everything is set up more or less from the beginning, there will be less complaints. So make a packing list according to what samples and experiments you want to perform. How many people do you need for this actual beam time? You want to work shifts if you want to make use of the beam time. Sometimes they have optimized systems if you do material characterization. In situ characterization usually requires you to be there all the time. And all have to register as users. So plan in detail, and then plan some more. You can never sort of get too detailed in your planning. It will probably not follow the plan, but still, if you have a plan, it's much easier to argue around that. Once the plan is ready, write and submit a safety approval form. So what will you bring to the beamline? This is where you tell the details to the synchrotron. Like, these are the samples we will bring. These are the hazards with the samples. The same with equipment. If you need to bring some pumps or fluid experiment stuff, you need to have that. They need to be inspected so that you don't plug in a faulty device in the synchrotron and it shuts down. What people you will bring, and be sure that they have registered as users. And do you need access to a chemistry lab while doing the measurements, if you need to do sample preparation directly there. So that's the SAF. Then you have training courses. So they won't let you in to do experiments and press any buttons if you haven't done a couple of this. Cybersecurity before you connect to their network, which is super secret and government owned. At least in the US, it's like you get, it's very keen on this. Cybersecurity part. Radiation safety, of course. It's a radiation facility. You need to know what X-ray radiation is. Synchrotron orientation, like what is where, which sort of contracts they are running under, and what is the mission of the synchrotron, and so on. User safety, of course. If a fire, medical emergency, spills of chemicals, who to contact, and all these things. So these need to be completed, usually 1-hour courses online that you can do from wherever. So just do them in time so they can see that, okay, everybody in the team has done the courses, they are ready to do measurements. So take the required courses, book housing. Don't come there and realize, oh, but how we're going to sleep. There are no sofas here inside the synchrotron. They purposely did not place beds next to the beamline. So if you want to sleep there, you need to book accommodation. Since you're working shifts and want to measure as much as possible, you want to have accommodation there and not 50 kilometers away to be able to work efficiently. But they have guest houses at all these facilities where you can go quickly to and from the synchrotron. Book that in time. Make schedule of shifts. Do that in advance. Again, key thing for keeping the mood up the entire 96 hours. It's like, no, I don't want to work now. And then you're, yeah. So if this is cleared out from the start, you're working these hours, you are working these hours. And remember food and sleep inside the planning as well. It's easily forgotten in research in general. It's like, oh yeah, we should eat and sleep. So it's even good. Plan. Like, okay, 5:30 p.m. I'm ordering pizza from the online pizza place here. And you can check all of this out before you go there. You don't need to figure it out there. Like, oh, what do I want today? Maybe sushi, maybe. No, lay out the food plan as well, and you're done. You don't need to think about it more. And sleep as well. Don't schedule like, oh, I only need 6 hours sleep, so I only take 6 hours break here. No, because it takes time for you to go to the guest house, get ready, blah, 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 get into bed, then wake up, and actually wake up, and then wake up again. And it will not be 6 hours of sleep. And yeah, you might need more, and so on. Schedule this so that everybody is agreeing upon it. And then teach about the experiment. It's better if everybody actually knows what the experiment is about. Everybody has knows the equipment, what buttons to press for the actual experiment, and what we want to get out of it, because that also, then it's not one person that always needs to be there from start to finish. And yeah. So some team management. Of course, this is not required from the Synchrotron. I'm just telling you as a tip because of experience. So we have some team management. Now it's time to go to the Synchrotron. If you have everything, all the papers, everything you need, they will let you in. Get ready, have some team building. It's quite, I mean, it can be a fun activity actually for the entire group if you just make it that and not something that, we'll sleep. And make it fun. Yeah, if somebody needs to sort of adjust their time for taking the night shifts, allow them to do that. Yeah, and then it's beam time. And this, I will just go through this quickly now, what happens at the actual beam time. We have some kind of orientation. The beamline scientists say, hi, this is the beamline. Don't press any buttons until we have gotten the course done, because he will give a beamline specific training, like what buttons to press and when. But once that is done, it's just start measuring. You just do it, more or less. Press enter, switch sample, switch, press enter. If you're two people, you can. It's more fun as well, and you can also help each other, because when it becomes a little bit, you become a little bit tired. It sort of reduces mistakes immensely if both know what's supposed to do and they can correct each other. Like, oh, but you didn't put that thing there.
And if you're going to run for 96 hours, how many people do you need to run this operation sort of efficiently? Is it enough?
More than 3. 3 is sort of the limit, I would say, to make useful shifts when you do these longer stuff. I mean, it's helping with more. And this comes into another completely other debate, because then you also need to figure out what publications might come out of it, who should be on the author list, and blah, 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 blah. Because if you bring a team of 20 people, have everybody contributed to the research. This is the big thing that's always discussed in this field. Right. So I would say more than 3 people. Then you can, if you're 3 people, you can overlap, have like 8 hours sleep, 16 hours work. But it's still tough. So if you're 4, it's like, maybe you can do 12, and just work in pairs, for example. So, and yeah, you will get tired at some point, and will be very repetitive. And it's also good to switch up a little bit, and be, if you're 2 at the beamline all the time, the other person can also analyze the data. If you're already aware of how to analyze the data, doing it while measuring is also such a time saver in terms of the entire project. Because, again, coming into the previous issue, that you come home and then you wait 3 months by analyzing data, and then you look at data, oh God, we did everything wrong. And what about my thesis now? But yeah, working shifts, next shift coming in, all right. More coffee, more measurement, and this typically happens. They are not 100% working all the time. So yes, beam can be down, and you feel, oh damn it, our entire schedule is broken. And well, you need to be a little bit flexible as well with the scheduling and everything. And yeah, it might be that the beam goes down. Usually it goes back up fairly quickly, but sometimes it can be a while. It might be some problem with some on the storage ring side, and they lose the entire beam, and might be a day of work and maintenance, and you have lost quite valuable beam time. And yeah, that's unfortunate. It's usually they try to compensate you in some way anyway. Maybe you will get it next cycle. They try to schedule because you lost it last. But these are things happening. These are, I mean, there's very, it's amazing that these works. If you think about just how big they are and what precision they need to work all the time to have like 100% availability of the beam. And they need to upgrade and update things all the time, which causes, of course, new uncertainties if it will be stable or not. All right, but before you know it, your beam time is over. Beamline scientists come back, evacuate everything before the next users come, because the next users will want to measure from 8 o'clock sharp as well, so don't keep all your stuff there, don't measure until the last minute of your beam time unless you have talked to the beamline scientist. It's always good to keep a good relation with the beamline scientist, just know that. Don't yell at them if they don't answer the phone in the middle of the night. I admire the work they do, for sure, because it's tough to be on call for these beam times and having users being desperate, like, it's 2 o'clock in the morning, I'm sorry, it's Christmas Eve, but can you come down because we have an issue? They also have lives. But yeah, evacuate the beamline, copy all the data that you need, then it's really about analyzing your data. You come home with terabytes and terabytes of data, and you need to make sense of it by comparing with other samples. You can always contact beamline scientists if you have a good relationship. They will answer your questions quickly. And they will be, let them be a part of the entire process. It would be a lot easier. And then present results, and this is important part also. Once you have done beam time, getting results, publish them, conferences, papers, and acknowledge the facility where you have done the experiments, acknowledge the team that has been involved, including beamline support. And yeah, then you just ask yourself, when can we do this again? Because you don't remember all the bad stuff, you just remember all the good stuff, right? And then you just end up going there over and over and over again, doing the same sort of thing, and it becomes more or less routine, but still fun. So yeah, with that, I've gone way over time, but thank you all for coming to this seminar. If you have any questions, I will be around, and with that, yeah, thank you.